Hi, today I'm going to be discussing how to implement the DBSCAN algorithm from scratch in Python. And if you don't know what DB scanning is, it's a density-based scan algorithm, and these are the steps essentially. So the step one is given that, so first of all, let's discuss the input. Given that you have a set of data points and an epsilon value and min values, you have to group them into density-based clusters. So first you categorize a data point as a core point, bordering point, or an outlier based on the number of points within epsilon distance of it. So if there are, let's say min points is, or like min values here is 5, if you have a certain point and there are 5 or more points that are within min values of it, then you could consider it a core point. If it has at least one point within that distance, but it's not as much as 5, it's less than 5, then you call it a border point, and it's considered an outlier if there are no points that are bordering it or within epsilon distance of it. And then second step is you select the random core point. So I'm going to use this example here. Let's select a random core point like over here, and you assign it to a new cluster. And this cluster initially starts with only one point, and then it grows based on what points are density connected to it. So you add all of the initial points neighbors, and if there's a core point in one of those neighbors, then you select a random core point of those neighbors and repeat the process. And then you keep on doing this until you run out of points to add to a certain cluster. And then you obviously do it for more clusters. So now let's see the implementation here. So when we look at this data set, right, we have an array of many data points, and for each point we want to have 4 properties for it. So first, a point can be defined by which coordinates it is, by its type, and the type will be what type of density point it is. So if it's 1, then it's a core point. If it's 2, it will be a border point, and if it's 3, then it's an outlier. We also consider an array of neighboring points of a certain point. So it's direct neighbors, and we're going to assign that to neighboring points. And the cluster it has been assigned to, that is also a property of a point. So let's say there's 9 clusters, and let's say for this example, there are 2 clusters, and this blue cluster is cluster number 2. So this point is of cluster number 2. Now we have to start step 1, which is initializing all of the points as either core, border, or outlier points. This is our DBSCAN method, and it takes in obviously x, which is the input, which is a NumPy array of lists. And the list, it only contains the coordinates of the data points. So we will assign for each point in our data. So for each data point, we will find the Euclidean distance between the data and each and every other point with this Euclidean distance method. So let's look at this. So we feed it x, our given point, which we want. So for a certain point, we want to find its direct neighbors, which means that any point that is within epsilon distance of it. And so what we do is we loop through all of the points in X, which is our full data set, and we assign X at J as a point. We also assign the distance initially to 0, and we want to find the distance between X at J and our given point P here. So what we do is point of I has, let's say point of I is of length 5 or something. So point, it will look something like 33615. Let's say this is point of I. So it has length 5, and that means P of I also has length 5. So what we want to do is, for each element, we want to subtract it and square it, and keep on adding it to the distance, at the end of which we just find the square root of the distance from that point and point I and point P. So the distance from point, which is x at j, and P. If that distance is less than epsilon, then we could call it a neighboring point. We can call x at j a neighboring point of P. And because of this, we could append it to the neighboring points. So what we'll do is we'll find all the neighboring points of a certain point P with this Euclidean distance method. Now we'll also assign the type of the point. So remember, if the type is 1, then it's a core point. And it's going to be a core point if the number of neighboring points is greater than min points. So remember, if we have min points as 5, if it's 6, then that means that it's going to be a core point. If the min points is 5 and the length of neighboring points is also 5, then what we actually know is that we have overcounted the neighboring points by 1, because when we go through all of the points in X right here, we also consider P. So we've overcounted by 1, which means that we want it to be strictly greater in this case. So if the length of neighboring points, that means if it's less than min points, less than or equal to min points, but greater than 1, then that means it's going to be a bordering point, border point, and then otherwise it's just going to be an outlier. So now we have to loop through all of the data points, and note that we only consider a point to build a cluster around if the point is a core point. So if the points at I, if the cluster is 0, which means if the point is a core point. Remember, what we did here is we appended each point has its own cluster that it's initially assigned to. And what I did at first was I assigned the cluster here. The cluster is defined as 1, it could be assigned to cluster 1, 2, 3, etc. But initially, when these points have not been assigned to clusters, then look what I do here. I do 1 minus the type. So if the type of point, if it's 1, which means if it's a core point, then it will initially, its cluster will be 0. And if the point is a border point and if it's not been assigned to a cluster, then it's 1 minus type, which means 1 minus 2, it will be minus 1. So the cluster of an unassigned border point will initially be minus 1. So what we do is, if we found that core point which has not been clustered yet, so this is the difference. Why couldn't I just have used the points dot type here if I wanted to specify a core point? I wanted to make sure that the cluster is 0. So that means if a point is a core point and it has not been clustered yet, then only you start a cluster around it. So points at I, the cluster will be assigned to a current cluster. So current cluster is just an increment. So remember, if we're exhausted with all core points of a certain cluster, we move on to a new cluster. So this is essentially symbolizes that. And what we do now is we find all the neighboring points of that certain core point, and we want to grow those neighboring points. We want to recursively grow it to become a cluster. So let's say with this example here, we choose a certain core point, let's say this right here. We initially find uh, its neighbors, so that means only it and its neighbors will initially be a member of the cluster. And then we find any core points that are members of the neighbors. So any core points in the neighbors, you could then expand upon them, and so on and so forth. So what we do here is we find all points that should belong to a certain cluster. This is fed x as a parameter, which is all of the data points. Obviously, the current cluster number, the points, which is just a list of the points. I is just the current point we're at, so it's the current position we're at. And what we do is we initially assign the cluster members as the neighboring points of points at I. So let's say this points at I is, let's say I is 1, so we're on the first point, and let's say points 3, 4, and 7 are the neighbors of that point. So our cluster members will be 3, 5, and 7, or 3, 4, and 7. So now what we do is we assign I as 0, and this will be an increment that checks if we are done exhausting the cluster members. So if we are not done with looping through all of the cluster members, then we cannot stop expanding the cluster. We need to meet this requirement to stop expanding the cluster. So our expansion point, which is the point at which we're finding its direct neighbors, will be cluster members at I. So again, if we fed point 1 here at first, so find cluster points at position 1, and remember how I mentioned points 3, 4, and 7 are the neighboring points. So initially, when I is 0, cluster members at 0 will be 3. So we'll be looking at the third point to expand around. So now what we do is we check if the point is a border point. If it's a border point, then we don't want to do anything with it. We want to just assign it to that cluster, but not expand about it. Remember, a border point is only, its cluster is only -1 if it has not been assigned to a cluster yet. So we do that check, and we just assign it to the current cluster. We don't do anything else with it. Now, if the point, if the expansion point, if it's a core point and it has not been assigned yet to a cluster, meaning that the cluster will be currently 0 for it, then we assign it to the current cluster. So after that, what we do is we want to expand the cluster members. So add this to the cluster members. So cluster members, let's say it was initially 3, 4, and 7, and now that we've expanded upon 3, let's say 3 was also a core point, which means 3 met this requirement, and the neighboring points for 3 were 8, 11, and 18. So now what we want to do is we want to also add 8, 11, 18, which are the neighboring points of member 3, to the cluster members. And so now cluster members will be 3, 4, 7, and 8, 11, and 18. So then we just increment I by 1. And After this, we'll have a list of cluster members, and we want to keep on doing this until I is less than cluster members, which means until we've checked all of the cluster members. Remember, if you think that this might go on forever, we only check this, we only go through this loop, we only expand cluster members if the point has not been assigned yet to a cluster. So if the point has been assigned to a cluster, then you don't do anything to the cluster members, so it won't grow at that point. And so this will be our algorithm for DBSCAN. And now I'm going to provide some examples. Now we'll look at an example data set, which is X right here. So X it has 1,000 points, and they're mostly in blobs, and we hope that our DBSCAN algorithm will categorize them into 1, 2, and 3 blobs over here. So let's see what this DBSCAN gives us. Our DBSCAN method, we will use epsilon 0.2 and the min points as 5. So a core point is considered a point is considered a core point if there are 5 or more points that are within distance 0.2 of it. To know a certain point's type, you could do points at i.type, or if you want to know the cluster that it belongs to, then you could do this. So we'll make list clusters that has the cluster of each point. Remember, cluster in this case, it will have 5 distinct values. It will either be 1, 2, or 3 based on which cluster it will be, or it could be -2 if a certain point is an outlier, or it could be -1 if a certain point is a border point that does not belong to any cluster. So what we're doing right here is we're constructing a data frame that has initially the x and y coordinates of these, and we also add the clusters column right here, which is the cluster that each one belongs to. Then, since the values of the clusters are -1, -2, 1, 2, and 3, we sort them. So now they will be -2, -1, and then 1, 2, and 3. And then we replace the values, we call them outliers if the value is -2. So we replace them with outliers. And we replace a -1 with border points that don't belong to any clusters. Now that we have our data frame constructed, we'll just feed it into a seaborn scatter plot. And this is the result that we get. So these blue points, you could tell that they are outliers. We also have a few border points that don't belong to any clusters. As you can see, this is an orange border point that, although it is density connected to one point, this purple point is also a border point, but it belongs to this cluster. And so as a result of being connected to only one border point, this orange point didn't make it to this cluster. And of course you have these 3 clusters, 1, 2, and then 3. Okay, so now we're going to analyze the complexity of our DBSCAN algorithm. And what I just did here is, instead of our previous data set where we had 1,000 points like arranged into blob-like structures, we will have a varying degree of varying amount of points. So we'll actually do it 200 points, 400 points, so on until 2,000 points, so we can test how fast the clustering works. And this is what we get for our DBSCAN algorithm. As you could see, it grows approximately on the order of n squared, where n is the number of points. and the sklearn algorithm just blows it out of the water. So let's analyze what improvements could be made to our algorithm, and we do that by first analyzing the complexity of the algorithm. So as we could see in this first step here, for data in X, when we find the Euclidean distance, you have to check the distance from X, from a point, to every single other point. And we have to do that for all of the points. And so each time you do that, you're comparing with n other points, and you're doing that for n points, which means the complexity will be on the order of n squared. Then we go through this and we loop through all data points, and we see what condition we need to actually do more computations. So the condition is if points at I dot cluster is 0, which means if a point is a core point that has not been clustered yet. And so since there are log n clusters, which let's discuss the assumptions about our data set first. So we have two assumptions here. The number of clusters is going to be log of the number of points, where log is natural log here. So let's say you have something like e squared points, so like around 8 points. That means the number of clusters will be 2 if you have 8 points. If you have e cubed points, then you will have 3 clusters, and so on and so forth. And the number of neighbors that a specific point has, on average, is the log of the number of points in the cluster that the point belongs to. So if a point belongs to a cluster with e squared neighbors, with e squared points, then it will be expected to have e neighbors. Well, e is not a whole number, but we could round it to 3, right? So it's going to be expected to have 3 neighbors. And notice that the log of the number of points in a cluster that the point belongs to, well, the number of points in a cluster is going to be, as previously discussed, log uh, n over log n, because since there are n total points and there are log n total clusters, then that means for each cluster there will be n over log n points in that cluster. And so we could just substitute this for n over log n, and that means the number of neighbors a certain point has, given a data set has n points, will be around this number. And with that, let's go to the complexity here. So when we do this, when we check this step, we have to check if a point is unclustered and it's a core point. So since there are going to be log n clusters, which was one of our assumptions, you will encounter an unclustered core point only log n times. So we go through this log n times. Now let's do the expansion step. What will the complexity be here? Well, I am saying that it will be log of n over log n to the power of log n over log n. So let's make an illustration here. What we're essentially doing in this expansion step is, let's say we start, this is our cluster. Let's say that our first expansion point is the center point. So we're expanding, we're first finding the neighbors of this point. So we have 1, 2, and 3 neighbors. And you could see that each neighbor has 3 more neighbors. So first time it's going to be one point that belongs to the cluster, which is this center point. Then we add 3 more neighbors, and then we continue on adding. So next we add 3 to the 3 squared neighbors. So then we add 3 here, 3 here, and then 3 here. So we keep on adding 9, and then we will add 27, and so on and so forth. And remember, the number of neighbors that a certain point has is log n over log n. And that means where n is the number of total points in our data set. So if in this example, each point has 3 neighbors. So in general, what I'm saying is that each point will have log n over log n neighbors. And you will just be taking the squared, then the cubes, depending on the number of iterations. Like here, I only did it 3 times. Actually only 2 times. One time with the direct neighbors, and then the second time with the neighbors of the neighbors. And you could keep on doing that. And that essentially becomes an exponential process. And the number of iterations in that exponential process will also be log n over log n. So let's say a cluster has around 10 data points, or let's say a cluster has 100 data points. Then we will do log of 100. Then we will expect around 5 iterations of this algorithm to take place. So essentially what we get is this to the power this for our complexity here. And so this step is of this complexity. And remember, when we're doing this find cluster points, you will go through this function log n times, as I stated before. And so let's graph what this exactly looks like. And let's see if it matches our initial graph where we varied the number of points. And this seemed like a quadratic relationship. So let's see if we find that here. So as you could see, I have the x squared, which is the initial time for the Euclidean distance, where you're computing the distance from each point to every other point for all points. That will be x squared. Then we did the ln x over ln x, ln x over ln x to the power ln x over ln x. That is essentially the time it takes for the expansion algorithm to work. And we're going to do the expansion algorithm log n times. And so this is what our sort of graph looks like given the number of points. Well, it's not exactly this, but it's on the order of this. So one thing you could notice is that although this is an exponential operator, and exponentials, they eventually dominate any sort of polynomial, which is x squared. In this example, this will grow extremely, extremely, extremely slowly, which means for all practical purposes, this term, the second term, is much smaller than the first term. Although for very, very large numbers, let's say like tree 3, right? If you plug in tree 3, then this second term will be greater than the first term. But for practical purposes, this is just order of n squared. And we will see the plot of x squared. It almost matches the first plot, since this second term is very negligible for very small terms, which means this relationship is sort of, we could see why, depending on, it goes to the n squared, on the order of n squared, based off the number of points that there are. And so that's our complexity analysis. And for the next video, I might show some improvements, because the Euclidean distance is taking the majority of our time here. And to improve that, there are many methods, but we don't need to do the Euclidean distance computation for all of the points, actually, for this algorithm. So that's a point of improvement, which I will discuss in the next video.